All right, this is Concept E in our Acids and Bases unit. We're going to be focusing on ionization constants. These constants are going to tell us how strong an acid or base is, and we're going to be using the concentration of aqueous ions in the solution to determine these ionization constants. We've done this back in our equilibrium unit when we did equilibrium expressions and solubility product expressions, where we weren't inputting any pure solids or liquids, and that's going to hold true for this as well. So Ka is referred to as the ionization constant of an acid. If you look on the very last page of your note packet, you're going to see an old table L from a previous New York State reference table that we're going to be using and inputting some of the data from. And again, this tells us the relative strength of an acid. All right, under the Arrhenius theory, we know that acids are going to ionize into a proton and then the leftover negative ion, where we're more concerned with this positive hydrogen. Remember that we're always multiplying our concentrations of any reactant or products over the concentrations of our reactants. And just remember, if we do have any coefficients out in front, that those get raised to that power. Under the Bronsted-Lowry theory of acids, we know here that we're looking at a transfer of a proton from the acid to the base, and in this example, producing hydronium and then that negative ion left over. So again, concentrations of our products over concentrations of our reactants. So again, this is going to influence how we're setting up our formulas. Now, the larger the ionization constant of an acid, the greater the percentage of molecules that ionize, so the stronger the acid. Not all acids completely ionize into water. We're going to see that looking at table L, if an acid is strong, it's in that top 5, it can ionize completely, making Ka too large to calculate. So HI, HBr, hydrochloric acid, nitric acid, sulfuric acid, these are all incredibly strong acids that basically ionize completely. However, these other ones that are on the list do not. So there's only a certain percentage of their molecules that actually ionize in water, producing an acidic solution. Now, one way to analyze this is using percent ionization, where the concentration of our hydrogen ion over the concentration of our entire acid times 100 is going to tell us how much is actually ionized. So in a 0.035 molar solution of HNO2, it only contains 3.7 times 10 to the -3 molar proton ions. So calculate the percent ionization. So how much of that original solution actually ionized when it was mixed with water. So here we have our formula. Again, filling in the hydrogen ions over the whole acid's ions, giving us a percent ionization of 11%. So only 11% of that original acid, when placed into water, ionized and influences the pH of the solution. Now, using Ka, we want to now find the concentration of the hydrogen ions. So calculate the protons of a 0.1 molar solution of acetic acid, and here we're given the Ka value. So we first have to just look at and analyze the formula of this acid. Okay, here we have the acetic acid breaking up into protons and the acetate ion. We're going to assume that H plus is equal to the acetate ion, which we're going to be assigning X. So this is important because we know that for every one of these that actually does break up is going to produce one proton and one acetate ion. So this should look very similar to our equilibrium constants. We have our concentrations of each of our products over the reactant. We're going to be assigning both of the products X values that we determined up here, putting this over the concentration of the whole acetic acid solution and saying that equal to the given Ka value. Going ahead and solving, we find that X is equal to 1.34 times 10 to the -3rd molarity, which this is our concentration of hydrogen. We could also then take that and plug it in for our percent ionization to further analyze it. All right, here we're moving on to just simply the ionization constants of bases. Under Arrhenius theory, we know that we're giving off this hydroxide ion. Just keep in mind that our reactant here is a solid, so it's simply just the product of our two bases. Under the Bronsted-Lowry theory, again, we know that bases accept protons from the Bronsted-Lowry acid. So again, though, based on our phases of our two reactants, we just have the product of the two products in our reaction. Finally, ionization constants of water. Pure water conducts electricity poorly, therefore must contain some type of ions. And this actually comes from the self-ionization of water, where some of the water molecules are actually ionizing in solution. Now, according to Arrhenius, if water is ionizing in solution, it's producing H plus and OH ion. So Kw is equal to the concentrations of our proton times concentrations of hydroxide ions. According to Bronsted-Lowry, very similar type of thing. If we have two molecules of H2O that are reacting together, one giving up a proton, one accepting it, we make H3O plus or hydronium plus hydroxide, which we can see then by Kw. Now, keeping these two formulas in mind, which are essentially the same thing, we know from tests that Kw, or ionization constant of water, is equal to 1.0 times 10 to the negative 14th. In pure water, only hydrogen and hydroxide ions are made, so these must exist in equal amounts in order for water to be neutral. So we know that then, if we are working with our two formulas for the Arrhenius and Bronsted-Lowry, that this has to be, both of these, equal to 1 times 10 to the negative 14th. Now, if we set this up and we find the concentration of our proton or hydroxide, and they have to be equal to each other based on the fact that for every 1 water this breaks down, we can set each of those concentrations to 1 times 10 to the negative 7. Now, what this is all telling us, and it arrives us at, is a formula we were going to be using in our next unit, which is the pH is calculated by the negative log of the concentration of the protons in solution. In pure water, we know that this concentration is equal to 1.0 times 10 to the negative 7, which gives us a pH of 7. So we're going to be working a lot with pHs. The last couple of slides are just kind of the rationale behind how we're going to be doing this, but definitely make sure you know how to set up the ionization constants, and we'll be practicing a lot with that in class tomorrow, and then using these last few slides in our following lesson on the pH scale. Alright, so there is no quiz or summary that you need to do for this unit, so you can just make sure you review your notes before class again and come ready to start.